Welcome everyone to this week's seminar. Today we are very pleased to have a visiting professor and lab alum, Dr. Reza Rouhi, speaking today. So Reza earned his PhD in the HPL, working with Drs. Epstein, Herzog, and Sudak. He joined the University of Ottawa in 2006 and moved to Amir Kabir University of Technology in 2011. His research interests include continuum mechanics, tissue mechanics, and tissue mechanobiology, all with applications to orthopedics and dentistry, specifically looking at implant design. So part of his research program is focused on developing more mechanistic models of bone remodeling and resorption processes. And we'll be hearing about some of that work today. And he'll be presenting a critical review on some bone remodeling and resorption theories and their applications to orthopedy and dentistry.
Thank you. Thanks for the introduction. It's a great pleasure to be here again. I'm very much excited and happy. I hope I can provide a useful time for you during my talk, and hopefully after my talk, I can learn from you, dear audience. Okay, a critical review on bone remodeling and resorption theories, applications in orthopedy and dentistry. In this presentation, first I'll briefly review bone anatomy and mechanics. Then we will see that bone is a smart material and a structure. I'll review trajectorial theory as well as Wolff's Law. Then I'll answer the question of why we need to know bone remodeling theories or models. Then we'll look at some well-known theories on bone remodeling. We'll hopefully together criticize them and revise them. Then some projects executed under my supervision or by myself on the applications of bone remodeling models in orthopedy and dentistry will be introduced and discussed, of course, briefly. And finally, discussion and conclusions. At the macroscopic level, we have two types of bones in our body. The cortical bone or compact bone, which make the outer shell of our bones, is made by a combination of hollow cylinders, so-called ostean or Haversian systems. In each ostean or Haversian system, we have a combination of hollow cylinders called lamellae, 20 to 30 lamellae. We can see just microscopic porosities in cortical bone. In the cancellous bone, as you can see, we can have very large porosity. In the case of osteoporosis, can be even up to 90%, 85, 90%. The spongy bone is a network, we can say in a sense, a network of interconnected plates and rods. In the areas which we have less stress, we do expect to see rod-like structures. And when the stress is high, we see plate-like structures. In our body and in our bones, we have actually in this hard biological tissues, we have, of course, different kinds of cells. The dark blue here is the bone matrix. We know that bone is a porous structure, so we have porosities and the solid phase. This part is a solid phase, and these cells are called osteocytes. As you can see, there are connections between these osteocytes as well as these osteocytes and these actor cells. The actor cells reside at the interface of the solid phase and void. And due to non-expandable nature of hard biological tissues, we have just a positional growth, a positional remodeling, which means that all resorption and formation of bone occurs just at the interface of the solid phase and voids. Yes, these are osteocytes, which are located within the solid phase. And these are the actor cells, osteoblast and osteoclast. Osteoclasts resorb bone and osteoblasts make new bony material. Considering the fact that bone resorption and formation occurs just at the free surfaces, the interface between solid phase and voids, so bone free surfaces are extremely important from biomechanics point of view. We have 4 types of bone surfaces: periosteum, endosteum, the surface and Haversian canals. As I've mentioned, the basic unit of cortical bone is called osteum, and we can have bone resorption and or formation on this surface, as well as on the trabeculae surfaces, on the surface of a spongy bone trabeculae. In a sense, we can say that the interface between the solid phase and void in our bones is where medicine and engineer they meet, because we have formation and resorption there. Okay, here on the left-hand side, you see a stress-strain curve. We applied, let's say, load on a piece of bone. When we increase the load, so the stress would increase as well as the strain up to this point, which we call in mechanics as the yield point. If I load it, then unload it, the loading and unloading curves would be quite the same. So if I remove the load, I would go to this point, which means that if the stress is 0, then a strain is 0. But if I go beyond this point, if I increase the load, as you can see, the behavior is here is different from this one. The slope has changed. Then if I remove the load, at the end of the day, I see that loading is this guy, but unloading is this one. And at this point, the stress is 0, but the strain is not 0. What does this mean? This means that if I apply load on my bone and I exceed the yield point, of course, there would be permanent deformation and dissipation of energy, micro cracks production. Here in this figure, as you can see on a cross-section of cortical bone, you see micro cracks here and there. In a trabecula of a spongy bone, the same story happens. So the bad news is that physiological nodes can produce micro cracks. But of course, it's not the end of the story. In 1987, in a scientific meeting, a German anatomist named von Meyer, he presented results of his investigation on the distribution of trabeculae of a spongy bone in the proximal femur. And this is what you can see, the results of his investigation. These are the trabeculae. In the same scientific meeting, a Swiss engineer named Kuhlmann presented results of his investigation on the principal stress distribution in a crane he had designed. And you see the direction of principal stresses in the crane that was designed by an engineer. Let me ask you a question. Don't you see some similarities between the proximal femur trabeculae and principal stresses in the crane designed by an engineer? They discussed about this similarity, and at the end of the day, they came up with a theory, so-called trajectorial theory. Trajectorial theory says that trabeculae are aligned with the principal stress direction. So trabeculae are not distributed randomly in this space. A spongy bone trabeculae are aligned with the principal stress direction. Another German anatomist named Julius Wolff took their theory one step further. Julius Wolff stated that not only trabeculae are aligned with the principal stress direction, but also if we change the direction of external load, the direction of trabeculae would change accordingly. Moreover, If we increase the external load, the thickness of trabeculae would increase. If we decrease the load, the thickness would decrease. So we are dealing with a quite smart structure. Yes, bone is smart. Here, in the yellow part, this schematic figure in the yellow part, as you can see, these are osteocytes. Osteocytes are connected to each other. Osteocytes are mechanosensors. And there's connection between this guy and this one, as well as these guys and actor cells, assuming that we apply load on this guy for whatever reason. Say, let's say, because of the microcracks, there is an interruption between this guy and this osteoclast. Resorption would initiate. So we have resorption process. If this is the end of the story, I'm sorry for my bones. It's not, of course, the end of the story. After resorption, there will be formation of bone. And at the end of the day, again, equilibrium state. So I have a brand new bone. Okay. In a sense, we can say bone remodeling is a control process. We have mechanical feedback in the remodeling process. Please assume a piece of bone, you apply load on this guy. There are sensors within the solid phase of your bone. These sensors would sense mechanical stimulus at the location of each osteocyte. Mechanical stimulus will be sensed. Then there will be some signals to osteoclast resorption, to osteoblasts formation. At the end of the day, a new geometry in three-dimensional space. So this guy, in a sense, we can say is an optimal structure. Is an optimal structure. We can say Wolff's statement, or we can state Wolff's theory in this way. Bone is an optimal structure, can gain maximum strength with minimum mass. So one way to model remodeling process is using optimization theories. You assume that bone can gain maximum strength with minimum mass. So it's an optimal structure. Simply speaking, we can say bone remodeling is bone resorption followed by bone formation. So if resorption is more than formation for a long period of time, then we would see a disease, so-called a silent disease, osteoporosis. Osteoporosis is because of abnormal remodeling process. Resorption is more than formation for a long period of time. So in order to tackle problems like osteoporosis, we bioengineers can contribute by using, by knowing bone remodeling model. There is no universally accepted mechanistic model yet. So we have to work on this ground. This is a very important question. Okay. I'm sure based on what I've explained about Wolff's law, you think why this happens from, let's say, mechanical point of view. If I increase the load, the thickness of trabeculae would increase. If I decrease the load, the thickness would decrease. So the density would decrease. So modulus of elasticity would decrease. So the strength would decrease. Why? Let's think about a thermostat. Assuming that we adjust the temperature of this room at a specific temperature, theta 1. If you have an increase in the temperature of this room, you should make AC to work in order to decrease the temperature. If you have a reduction in the temperature of the room, we have to make heater on in order to increase the temperature. Yes, I I can use this one as well as this one. Let me see which one should I use. Maybe this one. Yes. Assume that this is a structure. You apply load on this guy, and you're going to see what's the amount of, let's say, a strain, please. And you will see that maybe we should look at another mechanical parameter, let's say stress, strain energy density. I'll explain later on. Let's assume that I'm going to have a strain of this guy in a specific range or at a specific point, as we did for the thermostat. Okay? So if I increase the load, and if I wanted to have the strain in this range, what's the solution? Please help me. If I make this structure stronger, if I increase the modulus of elasticity of this guy, for the same load, the strain would decrease. And vice versa. If I decrease the load, then yes, I have to reduce the thickness of trabeculae. Each trabecular's thickness should be decreased. This is called mechanostat theory. The name was taken from thermostat. Okay, but there are many unknowns, many open questions, and you will see at the end of my presentation that there are many unknowns that we have to work on. In other words, and of course here you can see what I've explained as well. See, in the bone remodeling, the vertical axis, let's assume, is the rate of change of apparent density or rate of change of modulus of elasticity. Okay, we would like to have our bone in this specific range. This is a mechanical stimulus, but we don't know what this guy should be. Strain, stress, strain energy density, nobody knows, honestly speaking. Nobody knows. Let's assume a strain, okay? If the strain in my bone is in this range, I call it desired zones. Some people, they call it lazy zone. Resorption is equal to formation, so the rate of change of density is 0. If the load is below this, or the strain, sorry, is below this range, resorption is more than formation. If it's above this guy, formation should be more than resorption. If it's above this limit, then we have resorption, which is called overload. We applied very large amount of load, so we produce numerous microcracks, and the microcracks cannot be modified. Remodeling cannot compensate. So we have reduction in the strength and finally failure of our bone. Okay. I'm not going to discuss about mathematics of remodeling. No, I'm just going to explain about physics of the theories, a couple of theories that we are going to review together. I'm going to get your help, and we are going to go together and address some questions here. One of the most rigorous mathematical models on bone remodeling was proposed by Stephen Covin and his PhD student Hedges. When you have a porous structure, of course, you can ask, what's the volume fraction? Volume fraction is the volume of the solid part per total volume. Okay, volume of the solid part, bony part per total volume. This is important. This is important, of course, from mechanical point of view. We know that from mechanical point of view, the strength of our bone is owed to the percentage of the solid phase mostly. So it's important, right? They've assumed in their constitutive equations that the rate of remodeling is a function of volume fraction and mechanical stimulus. So let's say deformation gradient. But let's see whether this is a good assumption or not. Please consider two samples of bone with the equal amount of volume fraction, but different distribution of mass in the space. Let's 50% is void, 50% is the solid phase, but you have different way of distribution of mass in the space. So you can have different area at the interface of the solid phase and void. Considering the point that all bone resorption and formation occurs at the bone-free surfaces, do you expect the same extent of remodeling for these two specimens, two samples, please? Of course you don't, because the number of actor cells in these two cases would be different. So that the potential for remodeling would change. Okay, so we can replace, if you don't mind, if you agree, let's replace this guy with this one. We call it free surface density. Is the area on the interface of the solid phase and void per total volume. And after some mathematical manipulation, you can come up with this governing equation for the remodeling process. The good point, of course, there are some good points about this model. But I'm going to just mention one point, and that point is related to the surface remodeling process. The surface remodeling equation was proposed by Kovin and Van Busker. They did not prove this equation. Of course, in their paper, they've assumed m is equal to 1. Yes, this is correct, but just for the circular cross-section. If the cross-section of your bone is not circular, then using this formula, we can see that there should be a factor m here. This m is a function of the geometry of the bone. And this is in agreement with experimental observation. As was explained, we are producing actually microcracks during everyday serious and physical activities we have. So, and we know that microcracks can initiate bone remodeling process. Yes, this is a fact. This is well accepted that, yes, microcracks can initiate bone remodeling. So why not we define a factor, so-called microcrack factor, and enter this factor into definition of volume fraction? Because if I have cracks and if I define this guy as the area of the cracks over the total volume, I can change the definition of volume fraction. Agree? And then I use this definition of volume fraction and use continuum mechanics after some maybe lengthy mathematical manipulations. We can come up with this governing equation. I know most of you don't like this expression. I'm not going to explain about mathematics. I'm going to explain about physics of the problem. Let's work together. Integral of, this is the strain. Integral of strain, okay, dt, rate of strain, strain. What does this mean? That in the remodeling process, not only mechanical stimulus, but the rate of mechanical stimulus, as well as the history of mechanical stimulus, they are all at play. And this is in agreement with experimental observation, okay? And one lesson that we can take from our bones is that failure is a prerequisite for success, assuming that there is remodeling after failure. Another theory, which I'm going to briefly discuss, I hope I won't waste your time. This was proposed by Hoskas and co-workers, published in the journal Nature in 2000. The mathematics is quite straightforward. We have bone remodeling process, which means resorption, then formation, so rate of change of, let's say, volume fraction or apparent density is equal to the activity of osteoblast minus the activity of osteoclast. Very straightforward from mathematical point of view. We have a common sense about this equation, right? But the beautiful point about this equation is the first term. The first term, I mean here, this P. They've assumed that this this P is the stimulus which initiate and dictate the activity of osteoblast. But what's this P? This P is sigma Fi mu I Ri. I'll explain about physics of this guy. Is very straightforward. They've assumed that the activity of osteoblast is being dictated by the signals sent by all these osteocytes. This is the osteoblast, and is happy is going to make bone. And these are osteocytes. They send signal to this guy. Its signal is R. Let's say for osteocyte I is Ri. This is mechanosensitivity of osteocyte I. This is let's say. We call it a spatial exponent, this function. Let me forget about the name. This means that by increasing the distance from this osteocyte, the signal sent would decay exponentially. Okay, beautiful. And the prediction of this model is very beautiful. They publish in the journal Nature. Excellent. Okay. Let's see how we can revise this theory. Yeah, this is the signal that osteoblast would receive the signals will be sent to this osteoblast by this osteocyte, and he is happy. This is the stimulus, and then will be compared with a threshold value, thermostat. But this threshold value, based on recent experimental observation, we know that osteoblast would accommodate based on the temporal sequence of loading. If I apply a constant load, osteoblast would be bored. If I apply a decreasing load compared to increasing, compared to constant, at the end of the day, the osteoblast activity would be different. So based on this point, some researchers, they proposed this formula for this threshold value, the set point. So we can replace this K with this expression. And if we make computer simulation, we can see based on Hoskes and coworkers model, in the case of a constant load, we have a greater apparent density. Whereas by considering cellular accommodation effect, of course, we should have a greater apparent density in the case of decreasing load. So we might have some points here and some new insights based on cellular accommodation effect. As was stated, dear audience, I think a couple of minutes ago, in regard to the stimulus of bone remodeling, this is an open question. Nobody knows. Some are in favor of a strain, some in favor of a stress, some in favor of a strain energy density, but nobody could prove based on mechanical principles that which stimulus is the driving force for the remodeling. We worked on this problem, and we've considered just the first phase of bone resorption, which is caused by a chemical reaction between this cell osteoclast and this guy bone matrix, and this is the chemical reaction using the second law of thermodynamics. I'm not going to explain about mathematics. We have used mixture theory and second law of thermodynamics, and we came up with this expression as the driving force for the bone resorption. the beautiful part, or let's say points, are as follows. These two terms are mechanical: strain energy density, integral of sigma d epsilon, the area under the stress strain curve, okay? The second term is the hydrostatic pressure of the fluid phase. And the third term is related to the concentration of different ions before and after resorption. So we have chemical, biological, mechanical factors all together working in the resorption process, the first phase of remodeling process. So what's the stimulus? Honestly speaking, I am not sure if this is true or not, but this is based on the second law of thermodynamics. Maybe some new insight here. This is a basic question. Many papers, numerous papers have been published, but nobody knows. Nobody knows what's the exact mechanical stimulus for the initiation and control of remodeling. Okay. Here, let's assume that an orthopedic surgeon used a THR, total hip replacement prosthesis, because of the problem that was here, and replaced this guy with this one. But please note that this guy was made, let's say, by stainless steel. A modulus of elasticity is 200 gigapascal, and the neighboring bone is just, let's say, 10 gigapascal. 210. Please think about Wolff's Law. Would be some problems here, right? Another example. There is problem in the spine, and orthopedic surgeon can use this screw, pedicle screw, insert this screw into this the body of this guy, this vertebra. See, we have a very thin layer of compact bone, then the rest is cancellous bone. This is made usually by titanium. Modulus of elasticity 110 gigapascal, and the neighboring spongy bones modulus of elasticity is 0.5 sometimes. Think about Wolff's Law, please. In order to make a good sense to your mind, and this one, of course, we are not concerned about this one. A screw in a piece of wood, that's okay. Let's assume that I'm going to consider this prosthesis as this spring, and this one as my spongy or cortical bone. If I apply, let's assume they're arranged in a parallel manner. You apply load. Since they are parallel, the deformation of this guy would be the same as this guy. So the force transferred by this guy would be 1,000 times of this one. So you can imagine that we are actually shielding the neighboring bone from the mechanical stress. Our bones need to be under stress. So this is a problem in orthopedic as well as in dentistry, dental and orthopedic implants. And I was going to ask one question. So based on this point, should I design this implant, this prosthesis, and also, let's say, this dental implant based on just mechanical principles, just mechanical criteria? There are many research these days, even these days, in different schools, PhD, master thesis. They just use mechanical principles to see what's the stress distribution in the vicinity of the screw, what's the strain distribution, what? This is not enough, because our bones are sensitive with respect to mechanical stimulus. So we have to use mechanobiological laws and principles. In regard to dental implant, for example, we have made some very humble contribution. But again, I'm not going to explain in details about this because the time is limited. But the key point is that when if you're going to see whether your implant was designed properly, or say an optimal design of your implant, if you agree based on my explanation today, I think that if you agree, we have to make our implant in a way that can make minimum disturbance in the mechanical stimuli distribution within the bone. Agree or not? That's the point. In other words, if I'm going to see whether I have an optimal profile for this dental implant, I have to see when I insert this guy here in this bone, the stress here is close to the stress here. Even in that case, of course, I've made some mistakes because I've changed the normal mechanical atmosphere of my bone. Using the semi-mechanistic bone remodeling theory, we have made an investigation on osteoporotic bones. Based on experimental evidence, we know that in healthy old adults, there is a reduction in the number of osteocytes, healthy adults. Makes sense. So we don't have enough sensors. So at the end of the day, we should have reduction in bone density because we don't have enough sensors. But in the case of osteoporotic individuals older than 55 years old, it's very odd. Experimental observations show that there is a significant increase in the number of osteocytes. This doesn't make sense. We hypothesize that this can be due to the fact that the mechanosensitivity of osteocyte may decrease. If you have a reduction in mechanosensitivity of osteocyte, then if you make this computer simulation, you see the case that we have mechanosensitivity equals to 10% of the normal sensitivity of osteocyte, you see we have a great reduction in the bone density. We can also see the effect of overloading in a spongy bone using the same semi-mechanistic model I briefly explained. As you can see, if I increase the load, I have an increase in the apparent density of bone. If I decrease the load, apparent density would decrease. If I consider an abnormal increase in the load I apply, I can see a reduction in the bone density. Of course, there are many applications of bone remodeling theories in orthopedic as well. Let's assume that there is fracture in the distal part of the tibia, and orthopedic surgeons, they are wondering, they have to use intramedullary nail or let's say a locking compression plate. We can use computer simulation, finite element, bone remodeling theories, and we can see at the end of the day what will be the density distribution and changes in the strength and modulus of elasticity of a bone. Okay, based on my talk, I think you agree that we engineers need help from the other side, the medicine side. So mechanics need biology, and of course, biology needs mechanics. If you are going to work in the fascinating field of biomechanics, a mechanistic bone remodeling model is missed for sure. The model I've described was a semi-mechanistic. Let me briefly explain about different categories of bone remodeling theories. 3 categories: phenomenological model, mechanistic model, optimization-based model. Phenomenological model was Cohen's model. You look at bone, you look at bone as a black box. You change the input. You change the input, and you see the output. And then you make a relation between this guy and that guy. What's happening within this system? I don't know. I don't care. I cannot see. This is called phenomenological model, Cohen and many other models. Mechanistic model, yes, you change, let's say, the force applied in your bone. You're concerned about the apparent density changes, evolution in the density, evolution in modulus of elasticity, but you look at what's happening within the system. This osteocyte, how would react to the mechanical stimuli? This osteoblast, how would react? Osteoclast, what's the relation between these guys? This is called mechanistic, and we're in great need of a mechanistic model. We are not yet there. And optimization based, I already explained, I think. Bone is an optimal structure, so use mathematical methods, and you can find some good results with no insight about biology of this story. Okay. Yes, mechanical or mechanobiological based design criteria. I'm sure you agree with me, mechanobiological. Biological materials and tissues adapt their structures based on the mechanical and biological conditions and demands. Diseases such as osteoporosis, osteoarthritis, need bioengineers' contribution to be better understood. Collaboration between engineers or engineering and medicine side is absolutely necessary. New generation of implants should be designed based on mechanobiological principles, for sure. Last, I have to appreciate many graduate students and undergraduate students, as well as many fellows. I have to appreciate the University of Calgary, where I did my PhD, and my great supervisors, Professors Epstein, Herzog, and Soda. My former university, University of Ottawa, and my current university, Kabir University of Technology. I have, I think, 2 minutes based on the comment received from Michael. He told me that you can talk for 45 minutes, so 2 more minutes. I was wondering if I should talk about this or not. What's this? Of course, you can make a guess. There is a dark room, and somebody brought an elephant and put in that dark room. There were some people outside the room. They did not see an elephant before. And they were asked one by one to go into the room and come back and describe this guy. One went into the room and came back and described it as a big column. Another as a big fan, and so. There was a Persian poet named Rumi. He was born more than 800 years ago. This story was taken from Rumi, it's not mine. Then he said that I wish each of these guys could have a candle, and they could go together within the room together. And they could come back and describe this guy. And this guy is my bone. It's the bone remodeling process. I look at, from my point of view, in a dark room with no candle, very maybe weak even background in engineering myself, and almost no insight from biological side. Another researcher describe it as a, I don't know, a big column, another. And we are proud of ourselves that this is my model. It's the end of the world, but it's not the end of the world. They should work together. There is a proverb from Rumi, is very beautiful and is related to the bone remodeling process as well. Yesterday, I was clever, so I wanted to change the world. Today, I'm wise, so I'm changing myself. Our bones and remodeling. We have continuous change in the structure of our bone. So our bones are not only smart, but also are wise. Okay, thanks for your attention. Yes, please.
Thanks, Asa.
Thank you.
Really, really nice. I do have
Thank
a
you.
question that I can't kind of get the answer to, but
Yeah.
like bones have the option of both modeling and just formation. It's building bone on top of other bone, right?
Yeah.
But then they also undergo remodeling.
Yes.
Remodeling requires you to take out the bone, the old bone. So why would a bone? What's the utility of remodeling to build a stronger structure as opposed to just building new bone, which takes out half the process?
Very good question. Honestly speaking, as you know, modeling is the independent activities of osteoblasts and osteoclasts. So we can say modeling, in a sense, is equivalent to growth. But remodeling is resorption, then formation at the same spots. Modeling occurs mostly, I thought, just before maturation. But recently, I've increased my information and decreased my ignorance. And I found that even after maturation, there is modeling, but it's almost negligible. But remodeling is a kind of repair process. I don't know if I answered your question. Let me explain a bit more. You can ask, if my answer is not clear, please educate me. If I ask you, do you want to have micro cracks in your car or in your bicycle? I don't know if you have, maybe you have a car. In your car, while you're coming from your home to the university, of course, you don't like it, right?
Sure.
Okay, thanks. Yeah. Or the other question can be, if there are micro cracks during my talk within these walls, we'll be happy? Of course, we won't be happy. But why we are happy of having micro cracks in our walls? Why? When I have micro cracks here, is a sign that there is deterioration of material properties here. But it's not the end of the story, will be repaired. And you can say, why you didn't make a stronger material so we could not see any micro cracks in this material? Then I would say you should have 3 times lunch, 4 times dinner. Then that could be, you know, I don't know if I answered, but we can discuss that. I've found during the last 2-3 months, I found something in regard to remodeling and modeling that escapes me. I talked with Dr. Edwards, right? Am I right? In this regard, there are many papers, numerous researchers, they published paper, and some of us, we don't even know what's the difference between modeling and remodeling. We don't know. We just use, yeah, this is Huske's model. Let's use computer simulation. Then we publish something. But modeling as was explained, is very much different from remodeling. And my talk today was about remodeling. Remodeling is just the repair process. The repair process is from birth to death. Every day, we have remodeling in our bones. And our spongy bones, every 4 years, roughly speaking, our spongy bones are being completely renewed. Every 4 years. So 25% of my spongy bone this year would change, would be renewed. Please assume that we are going to make such a thing in this building, assuming in our house. Every year we are going to change 25% of the materials. We don't need, of course, because we don't have micro cracks there. We don't have this much periodic load, cyclic load on our bones. I don't know if if you're not happy, please go ahead.
Well, like I'm willing to say that I'd be perfectly okay with having micro cracks in my car if I could just like add more material to the frame.
So you're
like decreasing the area of the structure.
So you're very rich.
Yeah.
You're very rich. You know, from my point of view, would be a disaster because I cannot afford it.
Yeah, I think there is this interaction, but it's like very costly. It seems. You know, the remodeling process, it takes time.
Yeah,
you take bone away, you increase the porosity,
yes.
So you increase the localized strain.
Yeah.
You know, so it can, you know, it's this cyclical thing that maybe is useful, but at the same time, it has this component of like it's not beneficial as well.
Yeah, yeah. In other words, instead of working as a postdoc under Walter's supervision, you have to work on your car every single day. Because osteoblasts and osteoclasts and osteocytes, they are working continuously. It's amazing that osteocytes are mechanosensors, right? It's amazing. In 1 millimeter cube of our bone matrix, please make a guess. Who are the undergraduate students of Dr. Erdwan in this class? Undergraduate students. Yeah. Let me ask you one question. Okay, in 1 millimeter cube, I'm a very ignorant person. I'm just learning. I love to learn. I'm here to learn. So don't be scared. Micro cracks and failure is a prerequisite for success based on what we have learned today. In 1 millimeter cube of bone matrix, please make a guess how many osteocytes reside. How many? They are mechanosensors. 10, 100, 1,000, 10,000, 15,000, more than 20,000 in 1 millimeter cube of the bone matrix. So congratulations for being in this field, in biomedical. It's very beautiful. More than 20,000 osteocytes, if I'm not wrong. And they have communication with each other. And with bone forming and resorbing cells is extremely beautiful and complex process. And to be honest, as a person who worked for many years on the bone remodeling, I can say I know nothing, honestly speaking, because I just touched maybe the leg of that elephant. And I think that, so we have to work together. My message, my take-home message for the students, especially undergraduate students, is we have to learn. There are many unknowns, and there are great professors in this room, and I appreciate them for coming to this presentation, as well as great students. I do appreciate the students first, then the professors. They know more than me about engineering aspect, continuum mechanics, mixture theory. Then even on the engineering ground, I would say we are too far from the reality of I'm not working on articular cartilage, but I know a bit. Even on the engineering ground, we are too far from the reality of articular cartilage. We literally we know nothing. We know a little bit, so we have to work, and we have to stay positive and optimistic. Yes, please.
So just going back to like your implants and like the hip, and I was saying that it's way too stiff to pass the energy to the bone. What would you suggest hip replacements be made out of?
Excellent question. If you're rich, then you can use composite prosthesis, for example. Modulus of elasticity would be closer to, in my very humble opinion, I would say in the future, we should make prosthesis similar to the structure of the bone that we are going to insert within the bone. Biomimetics. I should take lesson from my femur and then make something very similar to this guy. We are doing this job for dental implants. And one of my PhD students worked on this project, and 2 MSc students are continuing because my PhD student, we could not find promising results there. He defended, and now 2 MSc students are working on that project. We called it biomimicked dental implants. Please consider a tooth. This is a tooth. And see how this tooth is connected to its neighboring bone. It's connected by this soft tissue called PDL, if I'm not wrong, periodontal ligament. We bioengineers, we make dental implant using what? 110 gigapascal. And we expect to have the patient happy of this kind of invention. And in the best case scenario, if we assume that this dental implant worked quite well, in the best case scenario, after 4 months in the mandible, 6 months in maxilla, if everything goes well, we have connection between this guy and the neighboring bone. So we can assume this is bony bridges. We call it osseointegration in the best case scenario. But how about the sensation of this guy compared with this one? Sensation for pain, etc. It's 50 times at least more sensitive than this guy. So we decided to make a dental implant, biomimic dental implant, by considering the same shape of our tooth. We take the shape of this guy, geometry of this guy, and we have used composite materials. We made this guy. Then we should use tissue engineering techniques in our lab and use a mesenchymal stem cell and other suitable kind of cells to differentiate PDL here, then insert into the mandible and maxilla of course, some animals, and see what will happen at the end of the day. So we have to learn, honestly speaking, we have to learn from our body. Our bones are extremely complex from engineering, even engineering point of view. if you just look at cortical bone, as a composite, I would say it's a very complex composite at different hierarchical levels. We have a combination of ceramic-like material called hydroxyapatite and collagen fibers. The dimension of this guy is a couple of nanometers, and this guy, the length is a couple of micrometers, the diameter nanometer. And this is the composite we see in our bone. And then you can look at bone as a composite, assuming that these osteons are the fibers. Because you have worked on bone, right? You can look at just one osteon and then look at the distribution of fiber in each layer of this osteon as a composite material. Who knows the governing equation? Please let me know. And then we make prostheses and implants, and we use in our bones, and we say, yes, we know everything. We just touched one part of that giant elephant. And that's it. I hope you're happy with my answer. Okay. Yes, Dr.
In one of the equations that you showed,
Yeah.
there was a parameter K, and I think that's the threshold about which the modeling is, right?
Yeah, yeah.
Is
Yes.
that parameter
Yeah.
well defined? Do we know what is that exact range that we want to stay with?
In the semi-mechanistic model, this one, this K?
Yeah.
Okay. This K, I think the computer simulations are mostly based on trial and error method, honestly speaking. We don't have a definite and solid figures and data for this guy, to the best of my knowledge. If you look at Hoskins and co-workers paper in the journal Nature, and in 2005 Journal of Biomechanics, they published numerous papers on this model. They've assumed a constant, but as was explained, this case shouldn't be a constant. Okay, I could answer you in this way. But before knowing cellular accommodation effect, before that, I think it's just based on trial and error. We have a long way to go in regard to this model as well. Coben's model, we don't know the constants in Coben's model, but our continuum, very humble contributions in continuum mechanics on adaptive velocity theory. The good point was that we could find some insights. That's what makes me happy, honestly speaking. The rest, I think I'm just wasting my time and energy, to be honest. Let me explain about another point in regard to the point I just mentioned in the resorption process. Yeah, we have suggested, we have proposed a mixture model, biphasic, then triphasic model on bone resorption, and I was proud of this while I was a PhD student here, but now I'm not only proud, but sometimes I think maybe I should work on another subject because yes, this is far from application. There is surely some values in there. In this contribution, let me explain a bit more. Yes. As I was scared, that's why I didn't put this kind of equations in my presentation, but since you have asked, I'm going to explain a bit. This model, the mixture model, could predict the anabolic effect of high frequency, low amplitude vibration on a spongy bone. High frequency, low amplitude vibration can increase bone density. 2002, published in the journal Nature by Clinton Robin and Stefan Judix from the City University of New York, I think. Yeah, University of New York. Nobody could find a theoretical explanation for this, but this theory can predict this behavior. This is a good point. So it means that maybe even though we just touched the leg of that elephant and by mistake I've described it as a big column, but maybe in the future some other would come and we can add the information together. Because this is based on second law of thermodynamics. This is based on, if I'm not wrong, consistency requirement for the conservation of energy in the mixture theory. Is not something that, say, I manipulated, so I came up with this equation. No, this is based just on continuum mechanics. So I'm positive that if we work hard and together, we can add information, and we have to have close collaboration. People from different sides, even in the engineering side, we have to collaborate. Thanks for your question. Yes, please.
I think I have a pretty, sorry if I don't agree. I think I have a pretty similar question with the thermostat, mechanostat example, that where you set a given temperature on your thermostat and it's always trying to get back to that temperature.
Yes.
But with bone, we know that bone structure changes over time. So what is it targeting in its thermostat to get back to?
In other words, if I'm not wrong, your question is what's the parameter to consider instead of that temperature to control it for the bone remodeling, right?
Yeah, but also how does our bone know what its target temperature is? This may be similar to the question of the constant.
How do we know? How do our bones know that this parameter should be controlled and how it should be controlled, right? To the best of my knowledge, open question. Open question. And I'm sorry for myself, but it's an open question. I didn't see in any papers, this, to the best of my knowledge, is an open question. But there are some hypotheses. And one point that is coming to my mind these days is that everybody says in this field, we assume then. We assume then. Why you should assume? Based on what? Based on what? This is based on the hypothesis which says that at the interface of matrix and void, we have bone lining cells. I didn't talk about bone lining cells. I apologize. Bone lining. I didn't talk about this, but it was not related to my talk. The scope of it. This is osteoclast, this is osteoblast, and this is bone lining cell. And this osteocyte, there is a hypothesis that we can quickly and see if I can shed some light. The question you asked, this osteocyte, it's like there was a hypothesis that this osteocyte and those lining cells, they make a picture of the three-dimensional arrangement of bone in our body. This is a hypothesis. So maybe based on this, then if there is a need to change the whole structure or internal structure, remodeling would be activated. If you have found the answer, please send me kindly. Yeah. There are many unknowns. I hope I didn't waste your time today. Professor Federico. Yes, please.
So I wanted to say, you mentioned before that sometimes you feel you should change job because the problem is so overwhelming and so complicated, and
yes,
that sometimes you feel you should change job. I just wanted to mention, I'm glad it's not just me. Oh yeah. I always have this feeling. So
we are in the same boat, yes, my friend. We are theoretical researchers, so that's why we are in the same,
exactly,
you know,
exactly.
form. See, okay.
Exactly. It's for dissipation.
Yeah, dissipation of energy. Yeah, and micro cracks maybe.
A lot of micro.
Yeah. Okay. Any question, please?
Just like
Yes, please. Yes, please.
I have a sort of practical question about the use of these remodeling algorithms in implant design.
Yeah.
So and you can correct me if I'm wrong, but I have the sort of impression that I don't necessarily need a very good resorption model to tell if one implant is better than another, because you can look at the stress shielding at the starting state. But where a model like this might be helpful, for example, is if it was accurate enough to tell who's going to resorb their bone and loosen the implant and who's not. So my question is there something I'm missing? Like, is there another use for a more complex resorption model? And how close are we to being able to make predictions like that clinically?
Honestly speaking, I couldn't get the basic point of your question. It's very complex, please. Yeah, I'm ignorant. Don't look at these equations. I'm very much ignorant. Please.
How far are we from being able to look at two people with an implant and say yours will loosen and it's bad, and yours will be okay for a long time? How far are we from being able to do that sort of thing?
If I wanted to be optimistic, at least 30 years, 40 years, to be honest. Yeah, based on my, of course, please consider I'm ignorant. I'm very much ignorant. Very good question, because we are working in order to get there, right? We are working in order to get there. A very practical question. We are too far from there, but we are moving. The good point is that we are moving. If I lost my hair, so I think that I have something. Is not useful in the clinics today. But see, let me tell you a very short story. Mechanostat was, everybody says, almost everybody. Mechanostat was proposed by Frost. Yes. Are you sure? Wolff Law. Are you sure? He proposed the theory, or he just collected some information, and he was a smart guy and lucky. Then he came up with Wolff's Law, which is very beneficial. He did not even propose a simple mathematical model. He was an anatomist. But we appreciate him. But Wolff is being seen, and everybody admired this guy, but many people lost their hair in order to have Wolff's Law. So we shouldn't be pessimistic. We should be optimistic. We should work. But me, as a very this is my heartfelt feeling as an, for sure, a negligible researcher, discardable researcher. I believe that if we are going to make useful contribution, we have to work together. We should not just think about making a small contribution, making some papers. We have to solve problems to help human beings. to help human beings. We have to work together. Why different universities in this world, they don't work together. Well, I think that I know continuum mechanics a bit. I have to learn from Salvatore and Dr. Epstein. I think, yeah, this is my model. What? Okay, we have to be humble, in my opinion, and we have to work together. This is a very important story. Okay, implants should not be designed using just mechanical principles. A message from an ignorant guy who worked for more than 15, maybe 20 years on bone mechanics, but ignorant, because this elephant is very giant and then very small. We have to work together. Well, I'm positive. I'm positive. We are on the right track, but we can be in a better situation. I do appreciate all respected audience for attending this presentation. I hope I didn't waste your time. And a special thank to Rouhi, who helped me yesterday. This will be recorded, this part, hopefully will be recorded. Okay, I'm not going to say. Last night, I think it was 2 a.m., I couldn't sleep. I was thinking how I should explain about Mechanostat. That's why I woke up at 2:30, I think, roughly speaking. And I drew actually this figure. Where is that? I'm saying that we are trying our best to understand something and transfer our ideas to other researchers. What was that? This guy, see, beautiful. It was drawn around 3 a.m., I think. And this one, see, because it was coming to my brain, how you are going to explain. And last night I decided to add this guy. If I didn't add this one, I'm sure that you couldn't get, these are very simple stuff for you, I know, but you couldn't get the basic point. So we are doing our best. We are doing our best, but we are too far and positive. Professor Edwards, you are going to ask me a question.
Sometimes I think it's funny when we talk about
I don't mind talk.
No. I'm thinking about these models of and how they're so purely based on mechanics and how we use terms like it's an optimized structure to its mechanical environment. And we say it's a smart process, but then it turns over so much to the point where you're replacing your trabecular bone every few number of years.
Yes.
It would be akin to somebody like creating an attic and then tearing it down every few months and then rebuilding it again, and creating an attic again and then rebuild it, and just it sounds like a stupid way to build a structure that's meant to mechanically support a system. So the only way I can reconcile the smartness of bone is when I start to think of its other important functions that have nothing to do with bearing load, and that is it being a reservoir for calcium. And only then does it then make sense for why you remodel instead of model.
Excellent.
And so I actually don't allow my students to use the term Wolff's Law in my class because Wolff did not propose an equation. All he really proposed was that bone remodels in response to very strict mathematical relationships, but he never proposed or said what those relationships were.
Yeah.
And so, and then to give him credit for such a law, I think is. So I encourage them to use the term functional adaptation.
Yes.
Functional adaptation. But I also think there's an element randomness to the remodel. Because it's quite stochastic.
Yes.
So I just want, maybe the question would be, is there a way that you can incorporate stochastic nature,
Yes.
the unexplained phenomena of how sometimes you see remodeling that's not happening in areas where there's micro damage. It doesn't happen in areas that are shielded from stress.
Yeah.
It just happens. Is there a can we incorporate that type of behavior into these types of mathematical models?
Very good points. I appreciate it. The first point that you have mentioned, yeah, I agree, but the time was limited. I couldn't speak about. Yeah, bone is a reservoir for calcium. More than 99% of calcium of our body is stored in our bones. So one good reason for remodeling resorption is to release calcium, as I explained in the resorption process. You are totally right. In regard to considering the stochastic way to look at bone remodeling, I think there are some efforts in this regard, but honestly speaking, I'm not in favor of that. I'm not in favor of that. I'll explain why, but I might be wrong. I'm ignorant, so I might be wrong. For example, in Hoskins and co-workers model published in the journal Nature in 2000, they have assumed that the second term in the remodeling, which is the activity of osteoclast, they've assumed that that guy, the second term, is the second term, d rho over dt is equal to the activity of osteoblast minus activity of osteoblast, activity of osteoclast. The second term, they've assumed that we can consider a constant probability for the resorption, because resorption occurs either because of disuse or overuse. In the case of disuse, everybody knows that we can use this equation. So the probability of resorption at different spots can be determined based on the stimulus received by this osteoclast from osteocytes. Okay, but for the case of overuse, in the case of overuse, we have resorption as well. They've considered a constant, I think 20 or 30%. And they explain that since we cannot predict, but bone is a non-homogeneous porous structure, so we cannot predict where resorption can be initiated. So they've considered a constant. After a couple of years, a group of researchers, they have found that the resorption process is also due to overuse, is also related to the signal received from osteocytes. I cannot understand why. Do you have any reasons why we have to employ a stochastic method? Any reason behind this? See, I'm not in favor of Hoskins and co-workers to consider for the overuse a constant number, because I cannot predict where microcracks, where resorption will be initiated. I'm not in favor of that, because based on experimental observation, because the probability of resorption is related to the signal received by osteoclasts from osteocytes. So I cannot understand why we should use a stochastic. I do respect your point. Because of my ignorance, I'm asking. Maybe is due to my ignorance that I didn't see any papers in this regard. And is there any reason?
Oh, I don't know. And maybe stochastic is maybe the wrong word, but Salvatore doesn't model every single orientation of every single collagen fiber in a particular part. There's a probabilistic distribution, right? And that's probably as good as he can get. And so I'm just wondering if maybe, that's not stochast, that's completely, this is different, I guess, what we're talking about, but maybe what we can do is we can model a probabilistic distribution of what this remodeling is happening.
Because of non-homogeneous and kind of random nature of a spongy bone.
Well,
It makes-
and just this whole biology thing,
Okay.
this remodeling aspects that presumably have nothing to do with the mechanical environment whatsoever.
Okay.
I mean, we get remodeling in the skull.
Won't be too difficult to go in that way, but it makes sense to me.
Yeah.
Because we have a very complex system. So maybe we can define a graduate thesis on this ground.
One thing that could be done could be to use the probability distribution.
Yeah.
For example, for the orientation of the trabeculum as a remodeling parameter. And although, since we know that they mainly go with the stresses,
Yes.
then it would be probability given in some way with you would have a peak about one direction, then a peak about an orthogonal direction.
Okay.
That would be more or less. So there will be some expression around that direction, I guess. And then you make those two directions evolve. You can throw those in a model, and that becomes the modeling variable, which again you can consider in the two possible ways as an internal variable as a separate additional dynamical variable. So you can do it a la Mojan or a la Wolff.
Yes. Yeah. Yes.
Oh.
I cannot understand.
Same for me.
Yeah, but Dr. Edwards' point was quite thinkable. Maybe I can define a thesis. If you are going to be a co-supervisor, I can define. And we can make Salvatore involved as well. If you agree, we have lots of students.
Sure.
Okay. Any
Is
other
there a
questions?
differential equation?
Yeah. Oh, okay. Yeah. Okay. Thank you.
All right, so please join us next week. We'll be hearing from Dr. Kenzie Friesen, and she'll be sharing some of her PhD work on softball biomechanics. See you next week. Softball.